Hi all, my name is Pietro Tullo, a master student from the Politecnico di Bari, and today I'll present my work named Numerical Study of Noise-Induced Convergence of IC Machines based on spintronic oscillators, in collaboration with Luciano Mazza, Mario Carpentieri, and Vito Pugliavito from the Politecnico di Bari, and Giovanni Finocchio from the Università di Messina. I start giving a definition of a combinatorial optimization problem, and in particular of the max cut. So we will discuss the IC machine, the spintronic oscillators, and the phenomenon of droplets. Also, I'll present the KURAMOTO model and our results. So what is an optimization problem? It is a problem of finding the best solution among all the possible solutions. A combinatorial optimization problem is an optimization problem with discrete variables. Also, we can classify different problems in some classes. For example, we can have class P, class NP, or class NP complete problems. We will focus on the class NP complete, but at first I have to give a definition of what is the reduction of a problem R to a problem Q. So given two problems, R and Q, if there is a polynomial algorithm that associates to each instance of R an instance of Q, in such a way that the solution of the instance of Q provides the solution of the corresponding instance of R, it is said that R reduces to Q. So a problem R in the class NP is called NP complete problem if each problem Q in the class NP reduces to R. For example, the max cut problem. Okay, the max cut problem is a graph problem. In fact, our approach is taking a system, map it with the graph theory, where we can see the vertices that are the elements of the system and their connections. Okay, and the next step is to map the graph with the matrix theory and then the implementation into the solver. So a weighted graph is a graph with weighted connections, and the cut is the bipartition of the vertices of the graph. So the objective of the max cut problem is to find the bipartition or the cut that makes maximum the sum of the weighted cut connections. Here we have some examples of a cut, okay, but not of a max cut. Here we have a cut value of 10. Here we have a cut value of 15, but both are not a max cut. Here there is a representation of a max cut where its value is 37, and here with the green line, so the max cut, okay, and here we can see the bipartition of the vertices of the graph, so the blue vertices, okay, and red vertices. The IC machine, so in that case, is a machine that can solve sometimes this kind of problems. So the IC machine is based on the Ising model that takes a weighted graph and uses it to define a scalar function that we can call the Ising Hamiltonian. Here there is the Ising Hamiltonian with two terms. The second term is the external field term that is equal to 0 if we want to map the Ising Hamiltonian to the KURAMOTO model. Okay, in the first term, instead, we have the elements of the coupling matrix, and here the spin values. The spin values -1 or +1. So at the end, we will have some vertices of the graph with the spin value of +1 and other vertices with the spin value of -1. So we will have two groups, a bipartition, so a cut. The objective is to find the spin configuration that minimizes the Ising Hamiltonian. A physics system that can do it naturally is the Ising machine, and here there are some examples like the coherent IC machine based on optical oscillators and the wave system solution, but both are complex machines, more expensive and also with a little adaptability. Our proposal is to realize an IC machine with spintronic oscillators that are highly tunable by a bias current and a magnetic field, Also, they are among the smallest microwave oscillators developed. And their simple structure is a key ingredient for on-chip realization. Here there is their structure. Okay, we can have a fixed layer, okay, or a pinned layer that serves as a polarizer. Here there is the current, so a non-magnetic dispersion, and here a free layer whose magnetization is excited into steady state oscillations. Here we can have a precession of the magnetization that gives us the resistance oscillations of the structure, and then the voltage oscillations that are represented into this figure. Okay. But not always the magnetization of the free layer is uniform. In fact, when the spins are pointing opposite to the ferromagnetic state in a small circular area, then this area is called a magnetic bubble with the blue color. With the white color we have the domain wall, and also with the red color we have the magnetization of the remaining part of the free layer. Red and blue colors can indicate positive and negative zeta component of the magnetization of the free layer. Another main characteristic of the spintronic oscillator, it can be that with the current variation we can have the output frequency variation, okay, and also we can modify the area of the bubble. But in some cases it was observed that the frequency is constant, or with the current variation, or it decreases very slowly. Okay, in these cases, if we take the Slavin model and its representation of the frequency, we have this term, the nonlinear frequency shift, that is near to zero. Okay, in this situation, in this case, we have the Slavin model that behaves like the KURAMOTO model. Okay, the KURAMOTO model, so it's very important because it can solve different combinatorial optimization problems, like the max cut. Okay, here a representation of the KURAMOTO model with two terms, the coupling term and the input signal term, the coupling coefficient, the elements of the coupling matrix, and here the phases. Here instead we have the amplitude of the input signal. The input signal that have the frequency input twice the central frequency of the network, and it can minimize the Hamiltonian according to the KURAMOTO model. In fact, in these cases, we have the injection locking, that is the oscillator synchronization to an external wave signal. Here we have a representation of the associated energetic function of the KURAMOTO model, and then the Ising machine can minimize the energetic function. But we have that in some discrete points that have 0, pi, and multiples, the energetic function coincides with the Hamiltonian. And then the Ising machine minimizing the energetic function also makes minimal the Hamiltonian, where the cut has a negative sign. Okay, so the objective of the max cut problem is to find the bipartition of vertices that makes maximum the cut and minimal the Hamiltonian. Here we have our results with the optimal values of the noise amplitude, where we have a very low time to solution, a very low quality index here represented, and also a very good percentage of correct results, that is near the number of the repetitions. This is 100. This for a cubic graph with 8 vertices, where a cubic graph is a graph where each vertex has only 3 connections. In this case, we don't have annealing because the parameters of the KURAMOTO model are constants. Here there is a solution of a max cut problem for a cubic graph Here we have the max cut representation with the evolution of the cut in the time. Here the max cut value when there is the synchronization of the oscillators, okay. And here we have the discrete points where the KURAMOTO model coincides to the Hamiltonian, and then the Ising machine makes minimum the KURAMOTO model, also minimize the Hamiltonian, okay, and makes maximum the cut. Here we show that the presence of noise helps us to have a better result than the case without noise for a lot of for a system with a lot of vertices, a lot of elements, and then oscillators. But it is not enough, because in these cases it is useful the annealing technique, that is, so the variation of the parameters of the KURAMOTO model. So we can see here the our annealing technique applied to the system, and the annealing can help us getting out of the local minimum of the energetic function of the KURAMOTO model and go toward the global minimum of the function that gives us a better result than the other two cases. So, conclusions: spintronic oscillator-based IC machines can be very useful to solve combinatorial optimization problems. Also, noise. It was observed that noise helps the system to converge towards the energetic minimum, and also our annealing technique allows a better approach to the optimal results. Thanks for the attention.